Welcome. This video is going to talk more about redox equations and something known as the oxidizing and reducing agents. A reactant that accepts electrons, that means it's being reduced, is called an oxidizing agent because as that particular compound or element is accepting electrons, it means somebody else is losing electrons and becoming oxidized. So the reactant that's being reduced is known as the oxidizing agent because it causes another reactant to become oxidized. Remember, one can't happen without the other. So likewise, a reactant that loses electrons or supplies the electrons is called the reducing agent because as it's being oxidized, another compound or element is being reduced. So again, a species that is reduced is also known as the oxidizing agent. And the species that's oxidized is called the reducing agent. And, think of agent as somebody, who helps you. Your insurance agent helps you with your insurance needs. So whatever's being reduced is an agent for oxidizing another compound. And instead of using the word agent, you can also use the words reductant or oxidant. So if we look at this example, we're being asked what is oxidized and what is reduced. So what we first need to know is the oxidation states for each element here. Carbon is easy, it's going to be 0, but on this side it's going to become a +2. Oxygen, since it has top priority among these three elements, is going to be -2 on both sides. And iron's going to go from a +3 to a 0. So that lets me know that iron is being reduced because its charge went from +3 to 0, it gained electrons, whereas carbon is being oxidized. So what's the oxidizing agent? Iron's the oxidizing agent, and carbon is the reducing agent. Whether a species will act as an oxidizing or reducing agent depends on what it's reacting with, just like redox does. So it's all about activity. Is the thing it reacts with stronger and more reactive or less reactive? So H2O is one that commonly varies as to whether it's an oxidizing or reducing agent. So if we look at this first equation, we have Na going from an oxidation state of 0 to +1. That means Na is being oxidized, so water is playing the role of oxidizing agent. It's allowing sodium to be oxidized. Whereas in this second equation, F2 is going from 0 to -1. So fluorine is gaining electrons or being reduced, and water is what it's reacting with for that to happen. So now water is being the reducing agent. And if we look more specifically in each case, we could look at whether it's the hydrogen or the oxygen that's causing that to happen. In the first one, it's the hydrogen that's allowing it to happen, and in the second one, it's the oxygen that's actually undergoing the change. So metals tend to lose electrons, become stable, because remember they're large, they have that low electronegativity and low ionization energy, so they tend to oxidize and serve as reducing agents. A more reactive metal is going to be a stronger reducing agent because it's going to be able to force its electrons on other elements more often, and it's going to be less likely to accept electrons. So the metal activity series, remember it's the list of most reactive to least reactive metals. It really is listing metals from the strongest reducing agent or the most reactive to the weakest reducing agent. And carbon and hydrogen actually are often included in these metal activity series, even though they're nonmetals. They can both serve as reducing agents. Hydrogen because it only has one electron and just the one shell, the 1s shell holding 2 electrons, and carbon because it's got 4 electrons. So it's got 1 in each of the orbitals, 1s and 3ds. So carbon and iron can both reduce, or carbon and hydrogen can both serve as reducing agents, and so they're often incorporated in. And a common use of carbon is to reduce iron compounds and other metals below iron in the activity series. And so it's called coking. Carbon and coke are virtually the same thing. Or if you've heard of smelting, this is the process that's done to extract pure metals from various compounds. So predict if the following reactions would occur or not. What you need to look at is which metal is an ion, which metal is in its elemental form, and is the metal in its elemental form, so in this case silver, strong enough to force its electrons onto zinc? And in this case, no, it's not. Zinc is the more reactive metal, so silver is not going to be able to replace it. But in the second one, magnesium is looking to unload its electrons, and it is stronger or more reactive than iron. So yes, that reaction would take place. Similar situation with nonmetals. Nonmetals tend to gain electrons. Remember, they're tiny takers, have that high electronegativity. So they tend to be reduced and serve as oxidizing agents. So a more reactive nonmetal is going to be a stronger oxidizing agent because it's going to be able to take electrons from more elements, and it's going to be less likely to lose its electrons. So we also have the halogen activity series that lists the halogens from the strongest or most reactive to the weakest oxidizing agent. And with the halogens, it's easy because it goes right in order that they're listed in group 7A, from fluorine, chlorine, on down the halogen list. So if we look at this one, ZnCl2 plus F2, would this reaction occur? So really what we're being asked to decide is fluorine reactive or strong enough to take electrons from chlorine? And the answer is yes. In the second equation, is iodine reactive or strong enough to take electrons from chlorine? And the answer is no.